Hello everyone, greetings of the day. I am Dr. Peeyush Kamlesh, and here I am going to present my topic is structural optoelectronic and thermoelectric materials for calcium-based novel half-usual compounds. So we have included these parts which we are showing in this content in the current PPT. So first we come to the introduction. So the term Husler derives from the name Frederick Husler, who studied such a compound in 1903. The first Husler compound was Cu2MnAl, which was studied and consists of 4 FCC sublattices. These compounds are also known as full Husler compounds. So this was the first researched compound, discovered compound. So afterward, it was discovered that it is possible to leave one of the 4 sublattices unoccupied. Okay, so the remaining atom with 3 FCC lattices is known as half-Husler or semi-Husler compound. These compounds exhibits 4 F43M space group, and basically we have seen that there are 2 categories of half-Husler compounds which have been explored more, valence electron count 18 and valence electron count 8. We choose here valence electron count 8 materials because they are less explored. So the 8 valence electron count half-Husler includes many promising materials with a big variety of lattice constant and band gaps. So far only a small number of them have been investigated, so we chose to work on these systems. In earlier studies, Zhu Belmaud and Azenov et al, as well as Wong and Srivastav et al have done a lot of study on the half-Husler compounds, and they have showed various applications of half-Husler compounds in different fields, like in thermoelectric devices, in topological as a topological material, or as an indirect bandgap material, direct bandgap materials, semi-metals. So this literature review shows that a very vast studies has been done on the half-Husler compounds, which show that these compounds have potential for various fields. So literature review underscores a notable lack of investigation into calcium-based half-Husler materials having valence electron count 8. This breakthrough serves as a major catalyst for additional research and calls for an in-depth investigation into the fundamental properties of CaZnC and CaZnSi half-Husler compounds. So, present study involves an extensive investigation of their structural, electronic, and thermoelectric properties using Wien-2K simulation code, which is based on linearized augmented plane wave method to solve Cohen-Sham formalism. Right? So we'll use the Wien-2K simulation code to study these materials. Okay, what is it? It is a density functional theory based simulation package, has exchange correlation potentials. So there are many exchange correlation potentials. For this study, we used PBE potential, right? So full potential linearized augmented plane wave method has been used to investigate the properties. And what is actually density functional theory? So the total electron E of an interacting homogeneous electron gas in the presence of an external field created by stationary nuclei as a function of electron density. Hence, we call it as density functional theory. So this is the relation which is known as Cohen-Sham equation. It shows that the total energy is sum of kinetic energy and external potential energy, as well as the Coulomb potential energy and exchange correlation potential energy. Actually, we all know that the total energy is sum of kinetic energy and potential energy. So kinetic energy comes from the first term, and the potential energy comes from the rest of the terms of right hand side. Right? So potential energy can be in the form of external potential, in the form of Coulomb interaction, in the form of exchange correlation potential. Right? So this exchange term include all quantum mechanical terms, the last term EXC, right? So these are some examples of exchange potentials like LDA, GGA, hybrid functionals. These all are the exchange correlation functionals. In LAPW method, the unit cell is partitioned into known overlapping atomic spheres that are centered on the atomic sites and an interstitial region. So for the construction of these bases function, the Muffington approximation is used. We used it as 7 for both of the materials. Atomic like wave functions are used for atomic sphere region and plane wave in the interstitial region. Each plane wave is augmented by the corresponding atomic-like solution inside each atomic sphere. So these are the structural properties of both of these compounds. We see that the volume optimization curve, the curve between volume and energy of these materials, show a perfect parabola, right? And the bottommost point of this parabola shows the most stable structure. The energy corresponding to the the volume corresponding to the bottommost point of this parabola is the volume of the most stable structure. And from that, we found that the lattice constant of these two materials are 5.739 angstrom and 6.475 angstrom respectively, while their bulk modulus is 78.928 gigapascal and 47.140 gigapascal for both of these materials. Okay, so the calculated structure parameters are shown show a best agreement with the results. Results were compared with the earlier studies like Srivastava et al. We have discussed earlier. These are the electronic properties. The band structure curve of both of these materials are shown here for CZ and C and CZ and Si. We see that both of these materials manifest direct band gap of 1.186 electron volt and 1.067 electron volt respectively with TB plus TB-MBJ approximation. Actually, TB-MBJ approximation was utilized to enhance the band gap and make it more compatible or more comparable with the experimental or the previous studied values. Actually, band gap defines the further study of various properties of these materials. So if the band gap is true, or it is correct, or it is, you can say, near to the experimental one, then we can find most of the properties very accurately as compared to the experimental results. So our first priority is to enhance the band gap and make it more and more near to the experimental or the theoretical values studied earlier. This is the density of a state curve of these materials. Again, both of these materials show here the semiconducting nature, and we see that in CAZ and C, the near the Fermi level, we see that in valence band region, which is the left side of the zero, it shows that the majority of the contribution comes from the p orbital electrons of Zn. Not p, actually, it comes from the p orbital electrons of carbon atom near the Fermi level. After that, the contribution comes from the hybridization of p orbital of zinc atom as well as d orbital of same zinc atom and d orbital of Ca atom also. While in both cases it happens in the same way. In CZ and Si also the same, we can see that the major contribution in the valence band near the Fermi level comes from the p orbital of silicon, and rest comes from the p and d orbitals of Zn and d orbital of calcium atom, right? In the same way, in the right part of the zero means in the conduction band, the major contribution, you can see that it comes from the d orbital of calcium as well as s orbital of zinc, right? And in CH and Si, there is slightly a different behavior of silicon, and we see that in the conduction band maxima, there is a slightly greater contribution of p orbital of silicon in conduction band minima. So these are the optical properties curve of these materials, and we see that the uh, epsilon 1 value at zero frequency, it shows the dielectric constant of the materials, and here we see that CZ and Si has larger epsilon 1 zero value than CZ and C, means dielectric constant of CZ and Si is greater than CZ and Ce, and the static dielectric constant for these materials are found to be 8.722 and 13.704 respectively. Similarly, the value of threshold energy of epsilon 2 omega, which is can be seen from the B graph, is found to be 1.18 0.8 and 0.86 electron volt that pronounce the optical band gap of CaZnC and CaZnSi respectively, and we see that it is very near to the estimated band gaps of these compounds. So optical conductivity sigma omega, it is defined as the conduction of photoelectron in presence of electromagnetic radiation. For CaZnC and CaZnSi, it becomes maximum at 4.67 electron volt and 2.84 electron volt respectively. Then the absorption coefficient of the compound presents about the fraction of the incident electromagnetic radiation absorbed by unit thickness of that compound. So more is the absorption coefficient, more is the efficiency of the compound to send the electrons from their valence band to the conduction band, right? So it has been found almost negligible till 1.37 electron volt and 1.28 electron volt for CaZnC and CaZnSi respectively. These are the thermoelectric properties graphs, and we can see here the variation in CB coefficient, thermoelectric conductivity, electrical conductivity, you can say, not thermoelectric, electrical conductivity and power factor, as well as figure of merit with chemical potential. So these variations show that CB coefficient near the Fermi level, CB coefficient is higher at lower temperatures. You can see this purple line. Okay, so it is for 300 Kelvin. In graph A, I am discussing in figure 6. CB coefficient is higher at lower temperatures for both the materials, and comparatively in both the materials it is higher for CaZ and Si. Similarly, if we talk about the electrical conductivity of these materials, we can see here that at all temperatures it behaves almost same. There is not much variation with temperature in it, right? And in on both sides of the Fermi level, means whether in valence band or in conduction band, it increases with increase in chemical potential, and after reaching a certain value, certain peak value, it again starts to decrease, which shows the true semiconducting behavior of these materials. In figure 8, we see that it is for power factor, and we see here that power factor is higher at higher temperatures in both the materials, and for 900 Kelvin it shows a maximum value, and that too in the valence band region. The region which is on the left from the 0 is valence band region, and the region which is from the which is on the right of the 0 is conduction band region. So from the figure 8 graph, we see that the power factor is maximum for p-type compounds of these CaZnC and CaZnSi. Okay, and in figure 9 it shows the thermoelectric figure of merit for these compounds, and we see that for both of these compounds thermoelectric figure of merit is almost reaches to unity on at lower temperatures. It is higher, while as temperature increases it shows a decreasing behavior. Here I want to mention that this jet is calculated by you can say that, we can say that in the calculation of jet we use only the electronic contribution of the electronic contribution in the thermoelectric conductivity, while the contribution of photons is not considered in calculation of jet. So its calculation can be enhanced if we use the phonon part of phonon contribution in the thermal conductivity. So these values can be enhanced more. But since we have calculated it using bootstrap simulation code, and it takes it takes less thermal conductivity as negligible, so we computed it like this. So these are the numerical data of the peak values of some of the thermoelectric parameters of both of these materials. You can see here. So high fuel compounds are an exciting class of materials with an enormous potential of revolutionize future energy applications. These compounds are fine photovoltaic in the UV and visible range, which can be confirmed from the optical graphs. Although they block infrared and far infrared regions, high fuel compounds are potential thermoelectric candidates as their figure of merit almost approaches unity at room temperature. So these are the references. So we found that there is a wide scope of half-usable materials in renewable energy devices, especially in thermoelectric generators, as they show a very wide range of band gaps and can be used at different range of temperatures for good thermoelectric devices, as well as these materials can also be used for photovoltaic devices. So thank you so much for this exciting opportunity to the International Material Science Awards. Thank you again. Thank you.